We're going to breeze through the material in this first section pretty quickly. The ideas are relatively intuitive and are things that most students have seen at some point before anyway. If you need a quick review, then you can certainly go ahead and watch them or skim through the descriptions of each video and just pick out any one where the concepts don't sound familiar. So this is our definition of a set, right? It's an unordered set of objects. And if that seems a little vague, that's mostly because it is. It's based on an intuitive understanding of what an object is that can actually lead to paradoxes when we start trying to apply properties to it. Now, there is a more formal axiomatic definition of sets, but it's beyond what we're going to need at this level. So instead, we're just going to stick with this intuitive definition, which is the one used by George Cantor when he first started building the foundations of what today we call set theory at the beginning of the 19th century. So I've got examples here of three different notations that we can use to define a set. The first one, in some ways, is really kind of the most straightforward, if maybe not really the technically clearest. It's just to kind of say it, right? In this case, we're talking about the set of all integers between 1 and 5. Now, the middle one here is more explicit. I think obviously it's more mathematical. This version where we just list out all of the numbers, all of the elements of the set, I should say, is called the roster notation. And it's great, it works, but it does have some limitations. It's not always going to be possible to literally write out every element of the set. Some of our sets are going to have infinitely many elements. Some of our sets are going to be made up of things like all of the numbers between 0 and 1. Well, there's no way to write all of those out. So we will need something that, well, maybe not necessarily more concise, definitely has more flexibility. And that's what we have with the final example here on the right. This one is what's called the set builder notation. Right, and again, it's pretty straightforward, but let's break it down just a little bit here. First, one thing I want you to notice, and this is an important part of the set notation, regardless of whether you're using the roster or the set builder version, you have to start off with these braces, these so-called curly brackets, right? Please don't try to get creative and use anything else. Parentheses over here in the roster notation, for example, this, same thing, but with parentheses, that means something, right? Something completely different from what we're talking about here with sets. So you really need to be sure you're following all of the details. So the next part, this, in a sense, we're going to talk more about functions in a little bit, but in a sense, this kind of establishes the domain that we're looking at. So this set is going to be taken from the set of integers. Then that's followed by some kind of formula, an equality, some kind of description that narrows down exactly, in this case, which integers we're talking about. So here we're talking about all the ones between 1 and 5. Now, the way I would read this, I would say this is the set of all integers x such that x is between 1 and 5. Right? So we start off the set of, so you know I'm talking about a text. Then we describe the domain here. That's the all integers part. This line here, you can think of this line as being the part that translated to such that. And then we describe the inequality, the formula, whatever procedure is being used to actually define the elements. So one of the most obvious things we do with math, really anytime we're defining a new object or class of objects, is ask ourselves, well, what does it mean for two of these things to be equal? And in the case of sets, we're going to say that two sets are equal if and only if they have exactly the same elements. Keep in mind, I know this was mentioned back on the definition slide, keep in mind the order of the elements doesn't matter. Right? A set is fundamentally an unordered list. So I have here, kind of trying to stick with using our formal mathematical logic notation. This is how I would define a set using our more formal language, right? It's the set, two sets are equal if for all x, or for every x is in the first set, if and only if x is in the second set. So I've got three sets down here on the bottom row, and they are all equal. They are all fundamentally the same thing, written in different ways. The first two use the roster notation, but you notice, I mentioned this a minute ago, the order is different, and I don't care. They have the same numbers, 0, 1, 2, and 3, and that's good enough. And it's good enough for them to be equal. And the second one, or the third one here, this defines the same set using the set builder notation. And how do you determine if these are equal? Well, it can be a little tricky. If it's not hard here, if at all possible, when I see this one, I can think, okay, those are the numbers 0, 1, 2, and 3. And then it becomes easy to compare it to the roster version. So those are what sets are. That's what we mean by two sets being equal to each other. And the next step, we're just going to continue kind of breezing through basic set definitions, but talking about what it means for one set to be a subset of another.